We're watching the first lesson on mechanical systems. In this lesson, we'll be talking about what mechanical systems are, what machines are, and what work is. So I'll be giving you a couple of examples of things, and this will be an easy start to this challenging unit because you'll need to be able to calculate and figure out what machines work best in what situations. You need to be able to figure out where or how machines make things easier, etc. So before we start, I'd like to ask the question, can you give me an example of a machine? Now, hopefully you've thought of one, and hopefully they're ones that we're going to show you right now, right? So we have the car, that's a machine, the sewing machine, and the printing press. These are all things that make things easier for you, right? So you can say that they're all machines. They're all automatic things that make work easier. So in this unit, we'll be talking about the physics of simple machines, right? We're going to go down to the bare basics of what machines are. We're not going to be talking about how necessarily a car works, but we're going to be talking about certain things that are parts of a car that can be considered machines. So, what is a machine? A machine is any device that lowers the amount of force or energy needed to move something. A machine is any device that lowers the amount of force or energy needed to move something. So basically, if it lowers the amount of force needed to move something, you could also say it makes the work easier. Whatever you're doing, whatever work you're doing, if you need to use less energy or less force, then you could say the work's done easier. So then, what's work? Well, work is the measure of the amount of force used to move an object. And we can actually calculate work. We can calculate work with the calculation work equals force times distance, right? Work equals force times distance. And we've done similar calculations like this before, right? We've done pressure equals force, sorry, this looks terrible, force over area, right? We've done density, which is mass over volume. In this case, we're not dividing, we're multiplying. And so you may notice that we made a triangle for this one. We made a triangle for this one. I'll show you a triangle for this one to make this calculation just a bit easier. So work equals force times distance. F stands for force, and we measure force in newtons. So if I give you a question and I put it in newtons, then you should automatically know that I'm referring to the amount of force being used. Distance typically is in meters, right? And work is shown in J for joules, named after the scientist who coined the term. So this is important because units are important. When I ask a question, what is the work? You need to give me the answer in joules. If I give you the question, what is the force? You need to give me the answer in newtons and distance in meters. So you need to be able to know force is in newtons, distance is in meters, work is in joules. So this is the work-force triangle, right? Again, work in joules equals force newtons times distance meters. So I have this triangle, right? Work equals force times distance, right? So again, just like with any of the other triangles, whatever the question's asking, if it's asking for work, you cover up work, right? And you can see these two next to each other, so that's multiplication. If it's asking for distance, you cover up distance, and it's work over force. And if it's asking for force, you cover up force, and it's work over distance. So this triangle will help you solve these calculations. And so you don't have to memorize the equation, you just have to memorize the triangle. And then draw that on a question, cover up what the question's asking, and the triangle will give you how to solve it. Again, let's say I was looking for work. Okay, well, work equals force times distance because they're next to each other. So I cover up work, right? I don't see it, and it's force times distance. If I'm looking for force, I cover up force, and now I have work over distance. So this will work for those situations. And so hopefully you know this triangle because it'll make your life a lot easier. So Sheila has just arrived at the airport. She's dragging her suitcase to the luggage check-in desk. She pulls on the strap with a force of 190 newtons at an angle of 35 degrees to the horizontal to displace it 45 meters to the desk. Determine the work done by Sheila on the suitcase. So this is a question that has unneeded information, right? These are the types of questions that get a lot of students because they'll look at the angle right here. They'll look at the angle right here and be like, that's important. But it's asking for work. So I'm going to write down the equation first. Work equals force, right? Force times distance. Does angle involve in any of this? No. So I don't need that. So ignore that, right? Do we know what the work is? No, that's what we're looking for. So I'll keep that as W. Do we know what the force is? Well, we see the big N, so that's newtons. So that's 190, right? 190 newtons. Okay, do we have distance? Well, she pulled it 45 meters. Okay, so now I know I have the distance. So what I expect you guys to do is write the equation. And again, when we did Pythagorean theorem, when we did density, write the equation and then just substitute in the values. Then you can just solve it, right? So now I know it's 190 times 45. 8,550. So 8,550 joules. So I put a J there. Sorry, the writing looks terrible, but that's how you would do it. Now, a lot of times students don't write the equation, and they make mistakes. They'll put that 35 there because they think it belongs. But if you write the equation, you go, okay, what is my force? 109 newtons. What is my distance? 45 meters. Well, then you'll know that angle is not important. And so you can ignore that. So be careful with questions like this because I'll add useless information like that and make sure you're paying attention so that you know how to use the equation. Let's try another example. The amount of work needed to move a cart 125 meters was 6,250 joules. How much force was used to move the cart? Okay, so we have already been given the work and we've been given the distance. So see if you can solve this. So pause the video, see if you can solve it, and then we'll solve it together. All right, so again, we write work equals force, right? Force times distance. Okay, well, I know what my work is. 6,250 because this is the J. So that's my work. Okay, so I replace the W with 6,250 equals, well, it's asking for the force. It doesn't give me the force, so I keep the F. Right? Times, well, what's my D? Well, I found my D right here. That's my distance, 125. Okay, so now I know this. So it's F times something equals, F times 125 equals 6,250. Now, if you know algebra very well, you know I want F by itself. I want my variable by itself. Well, F times 125. So I have to do the opposite, divide by this number, which will cancel it out. But whatever I do to one side, I do to the other, right? Which gives me that. So I go 6,250 divided by 125. That gives me 50. So now I know that F must equal, so 50 equals our force. Now remember, there's a unit for force. It is newtons. So 50 newtons was used. There is another way to solve this, right? We can use our triangle. So I'll draw this poorly drawn triangle, like so. And I have work at the top, force, and distance. Well, I don't know what my force is, so I cover up my force. Oh, work over distance. Okay, work is 6,250. Sorry, 6,250 over 125. And again, that'll equal 50. Now remember, keep your units. Newtons, joules, meters. Okay? So that's how you would solve these types of questions. Let's try another one. While training for breeding season, a 380-gram male squirrel does 15 push-ups in a minute. Yes. So his body moves 8.5 centimeters for each push-up. That's up and down. Determine the total work done on the squirrel after doing the push-ups. Well, we know he does 15 push-ups, right? We know he moves 8.5 centimeters for each push-up. That's including the up and down. And we know that he has a mass of 380 grams. Okay. So we're trying to determine the amount of work done. So here is something I'm going to show you. If you are given the mass, grams and force can be used interchangeably sometimes. Not all the time, but for the use of this unit, and in this unit we will use grams and newtons interchangeably. So we have a 380 gram male, which can also mean a 380 Newton male squirrel. Okay, so then I go 380, so I know my force, so I do my triangle again, right? I'm looking for my work, I know my force, and now I need to find my distance. How do I find my distance? Well, it gives me 8.5 centimeters for each push-up. So I can find out how much work he does each push-up. So I know work equals force, right, times distance. So work is what we're looking for. Force is 380 times, well, one push-up up and down is 8.5 centimeters. Now, there's the other problem, right? Because if you look at our equation way back here, distance should be in meters. So how do I turn 8.5 centimeters into meters, right? Well, we know that 100 centimeters make a meter, right? So 8.5 centimeters is the same as saying 0.085 meters. So now I have meters. Now I have 380 newtons. 80 newtons, right? So now 380 times 0.085. So 380 times 0.085, boom, 32, right? He's done 32.3 joules. And that's how you find the answer. So this one's a bit more complicated because I gave you a unit. Well, actually, we're not done. Sorry. We have this amount of work for one push-up. This is just for one push-up. Well, we need 15. We need to go to 15, right? We need to go to 15 push-ups. So we multiply that by 15. Sorry, I forgot about that. 484. So that would be a very common mistake that students would make because I made that too, right? 0.5, yeah. Right? This would be a common mistake people would make. They would stop at the one push-up. They would stop at the one push-up right here and be like, that's the answer. And that's exactly what I did. But because it says 15 push-ups, one push-up is 32 joules, we have to multiply it by 15 to get 15 push-ups. So this question was challenging because first off, you need to know you can replace grams with newtons. Right? So now you know your newtons. Second, you need to know that in the equation, distance is in meters. So you need to be able to convert 8.5 centimeters into meters. And third, which is the mistake I made, you need to know that once you get the work for one push-up, you have to multiply it by 15. Now, you could have just multiplied the distances by 15 as well, and then done the equation here. But either way, you need to make sure the units are consistent. Distance should be in meters. So all machines can be made from simpler ones, right? All machines are made from simpler machines, all complicated machines. So here we have some basic simple machines. You may see these in your everyday lives. The inclined plane, or like a ramp, the pulley, the lever, the screw, the gear, and the wheel and axle, right? These are all examples of simple machines. Now, as we mentioned before, the car is a machine, but it's a very complicated machine. But it's made up of separate, simple machines. You got wheels and axles, you got gears, right? You got different machines combining together to make work easier. You've probably seen levers through door handles, through scissors, through teeter-totters. Screws, everyone's seen a screw in their furniture. Ramps, everyone's been up and down a ramp or at least seen one. Pulleys, a well. So these are all simple machines that exist in everyday life. And we need to understand how they work to understand how to innovate on them, how to build on them, how to combine them, how to make more advanced machines, how to make machines more efficient, how to make machines use less energy, or at least make us use less energy so that we can do jobs easier. All right, so we're going to do a little bit of worksheets on these simple machines and these questions in class, and I hope you learned something today, and I'll see you next lesson.